First of all, I would like to wish a welcome to all those who are joining us for this webinar. And today, this is an E-SWAN webinar from the European Space Weather and Space Climate Association, where we have a sustainability commission. And today, it's a pleasure to have with us Thomas Schildknecht, who is one of the world leading experts on space debris, space safety, and space sustainability. If I would start the list of all the commissions you're in, I think it would take more than 1 hour, because he has served on many committees, technical and policy-making committees, like the ESA delegation in the Interagency Space Debris Coordination Committee. But he's also deeply involved in the SUST delegation at UN COPUOS, United Nations. And he has incidentally also been a vice director of the Astronomical Institute of the University of Bern. So I forgot to mention that he's at the University of Bern, and just next to EC where I am now. And my name is Thierry de Dr. So today this webinar will be on a topic, very timely topic. If you have questions during the webinar, please write them down in the question and answers window you will see at the bottom of your window, and we will go through them at the end of the webinar. So if you have questions, please write them down and we will go through them at the end of the presentation. With this, I think we are ready to start. And so, Thomas, the floor is yours. And thank you so much for being with us.
Thank you so much, Jerry, for the kind introduction, and thank you for having invited me. So, warm welcome to all the participants here. I'm going to talk today about, one type of sustainability or region where we need to talk about sustainability, which is usually not so commonly known. There is this whole set of UN sustainability goals, 17 actually, but none, is talking about space. All of them are, they stop at the top edge of the atmosphere. So what I'm going to talk to you about is a bit about space debris, a bit about the research we are doing, all, with the aim to provide the scientific foundation for the sustainable use of outer space. So let me introduce the problem. So what you're going to see in the next few slides is on the left-hand side, always a view of the Earth from about 15 Earth radii, and on the right-hand side, a close-up of what we call the near Earth, the low Earth orbit region. And the white dots, these are the objects. 1960, we had, a bit more than a handful of objects in space. And if we go now along, 5 years later, there's quite some more. And we are starting seeing on the left-hand side some objects which are in high-altitude orbits. If we go along to 1970, we start seeing on the left-hand side a ring, a string of pearls, which is actually nothing else than what we call the geostationary region. That's a region in the equatorial plane where the orbital period of these objects is exactly 1 day. So they apparently stay over a region stationary. That's why we call them geostationary. Let's go along. 1980, more and more objects, particularly also filling the low Earth orbit region. 1990, 1995, 2000, 2005, and I'm going to stop here at 2010. If we look at these pictures, it's already obvious that there is hundreds and thousands of objects up there, and I can tell you most of them are not active satellites. The vast majority are debris. So what is the picture today? This here is showing you the objects, the population of objects which I would say we know by name. For these objects, we know their trajectory. more or less well. We know where they are at each point in time. We know where they came from, the launches, and so on. These are about 35,000 objects larger than 10 centimeters. And when I say larger than 10 centimeters, this is in the low Earth orbit region. For the region in the geostationary ring, the minimum size in this catalog of orbits is rather something like 1 meter, perhaps 50 centimeters. If we, look at the population of objects larger than 1 centimeter, we are talking about 1 million. I mean, a piece of 1 centimeter, why should we worry about this? I mentioned it on the top right-hand side. The problem is simply that the velocities of these objects in space are of the order of 8, 9, 10 kilometers per second. And you have a collision, let's say head-on, you get more than 10 kilometers per second. And if you have a piece of 1 gram or 1 cubic centimeter colliding with another one at this velocity, this will release the energy of a hand grenade. And it's not the best, thing to throw a hand grenade on, for example, an active satellite. So this is the main issue we have in space. The result here of these 1 centimeter objects is these are models based on observations. We don't have, the orbits of each of them. It's just statistical orbits. Where do they come from? This movie shows you one source of orbital debris, small size debris. This was a collision which happened in 2009 when an active satellite collided with an inactive space debris, also a satellite. And what you see here, the result of that collision were thousands and thousands of smaller pieces. And these pieces, they don't stay in the same orbit, but within a year, they were filling an entire shell over the entire globe. So a shell of debris pieces, which each and every one of these is going to be a threat for active satellite. This was actually a wake-up call. But it also shows something which, let's say, specialists have been predicting since many years, that this is going to happen. There will be collisions between active and space debris objects, or space debris and space debris. And what's happening here is that with each collision, you are producing a huge amount of smaller pieces. The number is increasing dramatically, and each of these smaller pieces can collide again, either with a small piece or with an intact satellite, and so on and so forth. And you know what's going to happen. This is the famous snowball effect, and we'll have an exponential increase of debris pieces. This has, by the way, been predicted by a good friend of mine, even in the 70s, and it's called the Kessler syndrome. Don Kessler was the one who said, yeah, this could happen in future. What can we do about it? First of all, of course, we need to know what's up there. And I show you here on the left-hand side a picture of the population seen from the pole. So the geostationary ring is now really a ring. This is the objects which in December 2019 were in the best, most comprehensive catalog we have access to. This is a US catalog of orbits, which is taken by many of my colleagues and the public as, okay, this is the truth. On the right-hand side, you see again the same data from the US catalog, but on top of them, you see in green fragments of 3 explosions which happened in let's say, transfer orbits between the low Earth orbit and the higher orbits. All of these green fragments They were not in the catalog. They're still, most of them, not in the catalog. We have been cataloging them for us with the help of our Russian colleagues. We have a close collaboration with Russian colleagues, at least at that time. It's getting more and more difficult, obviously, for the current geopolitical reason. What does it tell you? It tells you simply that no single data or information source is providing you the full truth. And if you want to avoid a collision with your active spacecraft and you have just the left-hand side picture, you may do a good job for that part of the population, but you have no clue about a good deal of the population. For example, these three breakups in elliptical orbits. By the way, these breakups were due to upper stages, so upper stages exploding. It's not totally clear what happened because, in principle, upper stages, if they're left in orbit, they should be what we call passivated. So there should be no fuel anymore in these upper stages, because if you leave the fuel in there after years or even decades, that fuel can explode due to aging effects in the upper stage. So this series of images shows you a ground-based observation, by the way, from our observatory near Bern, the Swiss optical ground station. The trails here. You see, these are stars because we have been following the debris pieces, and the exposure time was here of the order of 20 seconds. So that's why you see trailed stars. But each and every small point, I hope you can see them in the video here, each and every small point is a piece of debris. Hundreds of debris just in this small area on the sky. So these were actually observations we did about less than 12 hours after the breakup of one of these three upper stages that I was showing you before. So, what do we need? What is the scientific research, and why are observations foundational? So, we need obviously a sound understanding of the space debris population and the active spacecraft population as well through observations, and for the smaller sizes through modeling, which are still based on observations, but the observations are not good enough to provide you a deterministic orbit catalog. We need to know more about the current state, monitoring of small size debris. We need to know more about the nature of the debris objects, because the nature, what do I mean with that? I mean physical characterization, size, shape, material, and so on. Why? Because we need to have a good picture about this in order to identify sources. We need to identify new debris sources. For example, if we see these clouds, what is the nature of the sources? And the physics driving the proliferation of space debris. Again, identifying debris sources. Progenitors of debris clouds. Was that a breakup due to residual fuel, battery exploding, or even a collision event? We also see that spacecrafts which are aging, which are there for decades in the geostationary ring in particular, they tend the material on the outside of the spacecraft tends to disintegrate due to aging processes. It's a very harsh environment out there. You have a lot of hard radiation, and in lower orbits you have residual oxygen, for example. And finally, we need to come up with the future evolution. There's models, evolution models, but we need data to update and verify these models on a regular basis. Because these models are then used to come up with mitigation measures, for example, with rules, what should you do in order to mitigate space debris. So On the research side, we have a whole series of questions: population, how many, what's the size, what's the orbital region, what's the nature of the object, the sources and the sinks, physics, about the mechanisms of creation, evolution, long-term evolution, models, as I mentioned, and the approach is very straightforward. On one hand, we search for the debris, what we call surveillance. Then we determine their orbits in order to be able to do collision avoidance maneuvers, for example. And finally, we try to characterize debris pieces in particular. So I already told you we do that on one hand at our own observatory, and what you see here is really not let's say a fake. It's the real view on a sunny day of two domes of the observatory with the famous Bernese Alps in the background. We have a whole series of telescopes ranging from 1 meter to a very small one, like 20 centimeter. We are also using telescopes abroad. 1 meter ESA telescope in Tenerife, for example. It's an old style telescope, but a very good one for these type of surveys we are doing on behalf of ESA. We are partners in a network of telescopes in the so-called small aperture robotic telescope network, where we have telescopes in South Africa, in Australia, and in South America. These telescopes are run in a robotic fashion, but they are all doing the same thing, more or less. They're looking for space debris, they're searching space debris, and if they find something, they are following up their orbits. We also use laser ranging. So apart from looking at the debris just, in a 2D optical plane, once we have been finding these debris, we want to have a better orbit of some of these, and we measure distances with our space debris laser ranging system. This is particular to improve the orbits of risk objects. So in order to help conjunction assessment and to do just-in-time collision avoidance. What the hell do I mean with just-in-time collision avoidance? The point is the following, we have quite a series of measures to mitigate space debris, but there is a lot of space debris already up there. And in particular, there's a whole series, hundreds of large upper stages in low Earth orbit at 600 to 900 kilometers altitude. These upper stages are huge, 8, 9, 10 tons of mass, the size of a school bus. And if we find out by these type of measurements that two of these objects are on a collision course, nowadays we can do nothing. The only thing is what we can do is watch and enjoy the show. But collisions of massive objects are catastrophic in the sense that they are producing tens of thousands of fragments. So we need a just-in-time collision avoidance technology in future, which means, if we see something is on a collision course, we try to notch one of the two objects a little bit. We need high precision orbit so that we have to notch it only by 10 meters in the orbit. Could be done by, again, lasers or by, robots going up there and moving one of them a little bit, and so on and so forth. Attitude determination is another technique, another, let's say, important observable, because if we want to go there with a robot and take one of these debris and bring it down or have it burned up in the atmosphere, we need to know what's happening with the attitude of that object before we can go there and grasp the object. So here, this is just a time lapse of how this works. We are operating, by the way, day and night time, but this is a nice time lapse from a night session where you see we are following different types of objects, higher up, lower. This is a low Earth pass where we have to move the telescope quite fast. So this is what you see here on this diagram is the main result of more than 20 5 years of surveys we have been doing for ESA, for the European Space Agency, actually, on behalf of ESA with the 1-meter telescope in Tenerife. And what the picture shows you, on the x-axis, we have astronomical magnitude, which is nothing else than brightness. And astronomers have this strange, way of describing magnitude. So the higher the number, the fainter the object. And on the y-axis, you have the frequency. The red bars here in this histogram, these are all objects which are not in any of the catalogs, hundreds of them. And in particular, in the size range, and I put the size range here from 60 centimeters down to 10 centimeters. And this is a survey in the geostationary ring, which means roughly at 40,000 kilometers distance. Nobody would have seen this population if we would not have been looking at this region. If we look, and this is a particular representation of the orientation of the orbital planes, you don't need to know the details. It's nothing else than the orientation of the orbital planes, the inclination versus the right ascension of the ascending node. Some of the features you see in this plot, in particular, this this part of a sinusoidal here, this is due to natural perturbations of the orbits. But on the left-hand side, I encircle two, what we call clouds. And these clouds in the orbital plane domain, they're clearly indicating that something, a breakup event or a collision must have happened there. So they point to collisions or breakups. This is very fresh ones from the past few years, less than 5 years probably ago, and unnoticed. So there's no report on any explosions which would explain these two plots. So this is a way of identifying new sources of debris. When it comes to characterization, what is the type of debris we are looking at? We are using, for example, our 0.8 meter telescope here to some spectra. On the left-hand side, you see a spectrum of one of these debris pieces. Again, on the x-axis, you have the wavelengths in angstrom, and on the y-axis, the intensity. So this spectrum here shows a very distinct knee at about 500 nanometers. And if we compare that with lab measurements of, let's say, materials which are used on the outer side of spacecrafts, then the only material we found which has this knee, this really very specific feature at 500 nanometers is multi-layer insulation fall of spacecraft. We have been finding a lot of these, in particular in the geostationary region, and it's a clear sign that the outer shells of these satellites, which are protected with these insulation foils for thermal protection, over years, this thermal protection is falling apart and is floating around. Again, looks like not so much of a problem, but with the relative velocities up there, you don't want to be hit by one of these even small pieces with your spacecraft. I was talking about the attitude determination. What we do in this context is, we are applying classical astronomical methods, which are called light curves in this particular case. So we look at the variation of the intensity of an object, the magnitude of the object, versus time, with the idea that this variation has something to do with the rotation or tumbling of the objects. Objects like, multi-layer insulation falls, or it could also be pieces of solar arrays or whatever, or pieces of metal. And while they are, tumbling, they're brightening and they're showing variation in the intensity. This is a classical method which we also use for asteroids, for example. On the left-hand side, I show you a space-based observation of asteroids on the right-hand side, the light curve of this of such an asteroid. So here we want to assess the spin axis, the shape perhaps of these objects, in order to help, in particular, active debris removal missions or in-orbit servicing missions in case of still active satellites. So all of this is actually to be seen in, or can only be done in international, let's say, scientific networks. We are very closely collaborating with space agencies, in particular ESA, but we also collaborating with the French space agency CNES, with NASA, with JAXA, with the German DLR, and then a series of, let's say, scientific organizations. One is the International Scientific Optical Network. It's a network of optical telescopes, a large network of optical telescopes, which is organized by our Russian colleagues, Kaldish Institute of Applied Mathematics in Moscow. I mentioned this breakup events of the upper stages. This is a good example of a very fruitful collaboration. Without collaboration, we would never be able to come up from single observations with orbits, because we have to hand over these observations to colleagues, tell them, hey, we have been finding something. Can you have a look at it? Can you provide additional measurements so that we can improve the orbits? Because we have no complete network on one hand, and on the other hand, there is also, let's say, in many cases, we have weather restrictions and we can't do these follow-ups. So at the international level, this problem has become, a topic I would say, in the 90s. And in particular, because of European upper stages, in particular Ariane 4 upper stages, which were launched in the 80s of the last century, and which notoriously had breakups. And the Europeans, ESA at that time, were notified by the Americans, hey, you have a problem. Your upper stages are notoriously exploding. Europe had no way to see that, because at that time there were only two systems in the world which were looking up into the sky to find, in particular, ballistic missiles, but also satellites in low Earth orbit. Military systems, the US military system and the Russians had a similar system operating. But nobody else would know anything about, let's say, passive objects which were debris, like these upper stages. So the first initiative then came from US and Europe, ESA, to fund an interagency space debris coordination committee, which is a technical body of space agencies which wanted to address this debris issue. This was early 90s. Nowadays, this IADC, Interagency Space Debris Coordination Committee, is still existing. And you see the flags on the bottom of the member states. So I would say all the major spacefaring nations and space agencies are part of this body. And this body came up with a set of guidelines in order to limit the proliferation of space debris. And the guidelines were mostly focusing on making sure that nothing is exploding up there, making sure that you don't leave objects in particular regions. In particular, the geostationary ring was declared as a protected region. So if by the end of the mission, you in the geostationary ring, you should move your object out of that ring. And in the same way, the low Earth orbit between the upper part of the atmosphere and 2,000 kilometers should become a protected region as well. So IADC came up with a set of guidelines voluntary guidelines, which were then taken over in the UN COPUOS, the Committee for Peaceful Use of Outer Space, and became the UN Space Debris Mitigation Guidelines. These guidelines are, as I mentioned, of very general nature. They don't tell you exactly what to do. They just say, do not this, do no harm, there's these protected regions. You should not leave anything there. You should prevent, for example, explosions. Later on in 2009, 2010, the problem became more and more. There was more and more awareness about the problem, in particular also because of that collision I was showing you. There were some other incidents around the same time. In particular, there were anti-satellite tests, which produced a lot of debris in the low Earth orbit. And the UN COPUOS was then setting up the working group on long-term sustainability of outer space activities. We were working in this body for at least 8 years to come up with a set of 21 guidelines, which became famous as the 21 long-term sustainability guidelines of the UN. This is, of course, not the end of the story. You now have guidelines from UN, but what are you going to do with them? The situation in space changed dramatically throughout the past 10 years. What I'm showing you here is the statistics of the payload launch traffic into low Earth orbit, which is here defined as 200 kilometers up to 1750 kilometers. And you see the number of objects was usually up to until about 2010. We were talking about, a few dozen up to 100 objects launched. I would say more than, roughly 100 objects launched into this region every year. Nowadays, and you see that exponential increase, we're talking about not just 70 launches, launching perhaps 100 satellites, but we are talking about more than 200 launches, launching several thousand satellites per year, each and every year. And you all know what is the reason for this steep increase. It's the commercial satellites, and in particular, it's the so-called mega constellations. It's constellations formed by thousands of satellites. Commercial. Civil and defense stayed at about the same level, slight increase as well, but it's mostly this upcoming new space commercial traffic. When talking about mega constellations, it's really constellations, large constellations of much more than 1,000 satellites. And this is only a small subset of the entire picture. We all know SpaceX, the Starlink satellites. Currently, this is not currently, this is by December of last year. I have to update this slide almost every time I'm giving a talk about it. So by December, there were almost 7,000. There were 7,500, more than 7,500 Starlink satellite deployed. And by each and every week, there is another 2-3 dozen of these satellites deployed right now. So we're talking about constellations of the order of tens or 10,000. The plans of SpaceX are for another 30,000. There is 2 other constellations which are currently built up. Kuiper with about 3,300 satellites planned, and OneWeb with 650, higher up. Just about the plans, in the United States, there are filings, so applications for licenses of the order of 500,000 right now. Even if if there is even just a small part of these going to be realized, let's say 10%, we're talking about 50,000. There's currently 2 Chinese constellations which are set up, tens of thousands probably, satellites. There is plans in Europe for governmental European constellations. The Russians have plans on their drawing boards. So this is the current situation. Um, Apart, from being a problem in terms of space debris or collision risk, or let's say the problem of a limited capacity of space, because we need to keep distance in space. We don't know these orbits to the centimeter precision or accuracy. We know most of them only to a few hundred meters. So we need to avoid close conjunctions. It's like with the train system where you have a minimum distance between satellite. And if you, given by the current technology, you have that minimum distance, there will be a maximum capacity for some orbital regions. And that maximum capacity with the current technology might be filled in the region of the Starlink satellites. Apart from that, we have another, impact on society in principle. The question is, how do these satellite constellations have an impact on society? And probably all of you know this spectacular, string of pearls, which you can see still uh, after a recent launch of a bunch of these satellites from Starlink in this particular case. Um, yeah, you know, these strings of pearls are, on one hand, absolutely fascinating. But the question is simply, do we want to see these objects all the time, everywhere on Earth? No, it's nice to see them once in a while, but we are talking about, let's say, several hundred moving satellites visible to the naked eye, always, every night, everywhere, in the Saharan desert. Wherever you go, you will see these hundreds of moving satellites in the sky by the naked eye. So, question, is the pristine night sky a human heritage? How can we ensure the protection of this heritage? A totally different aspect of what's going on. For the scientists, it's even worse, because the light pollution and the radio noise from these objects may cut us from accessing the sky or accessing knowledge about our universe. You may argue, there were always satellites up there. Yes, but now we are talking about a totally different, magnitude in terms of numbers. It's really the numbers which matter in this case. Currently, there's zero regulation about, let's say, these type of pollution, dark and quiet skies. Um, the Outer Space Treaty, sorry for that acronym OST, the Outer Space Treaty, the treaty from the 60s, the most important treaty we have on international level, only guarantees freedom for exploration and peaceful use, free access to space, which means every, state may launch as many, satellites as they want, and there's freedom of scientific investigation in outer space. So there's zero regulation on that. And one point I really want to make here, when it comes to this type of, let's say, sustainability and the question about dark and quiet skies, it should be our societies, not private companies, which are deciding on the trade-off between the benefits of these large constellations, which are clearly there. We internet or whatever these constellations are providing, and the protection of the space environment and the dark and quiet skies as a resource shared by all humankind. Just a side, issue I wanted to mention here as well. But I guess you have some here. almost impossible. So this video shows you, I mean, it's a simulation, but based on evolution models, shows you what's going to happening with this cascading effect of collisions over just the next 200 years. And I can tell you, this thing is already completely outdated because it doesn't include these large constellations. So business as usual, even with the traffic model of, let's say, 10 years ago, is not at all sustainable. That's for sure. So what are the key elements for long-term sustainability of the near-Earth space? First of all, it's like here down on Earth, we need to avoid pollution by creating new debris. We need to prevent the creation of debris at the source. So one way of doing it is perform better collision avoidance with the active spacecraft, but that's only a small piece of the puzzle because most of these objects are not active. So we need to prevent any type of breakup events. Any kind of stored energy like fuel or batteries and so on and so forth can, eventually lead to a breakup, even decades after you left your object up there. But even most importantly is what we use here as a slogan as well on Earth, don't leave a trace, which simply means remove all your objects at the end of their mission. We call this a post-mission disposal. But what means disposal? It's like here, are we putting our waste into a dump? Are we burning it? Whatever, and all of these methods have their pros and cons. In low Earth orbit, we are asking for atmospheric re-entry a certain number of years after the end of the mission, and in higher orbits like the geostationary orbit, we cannot, simply because of the energy budget, not afford to have them burning up in the Earth's atmosphere. So we dispose them in graveyard orbits. It's not the best solution because graveyard orbits are like, waste dumps here. After years, this graveyard may be leaking because of debris created in the graveyard and again proliferating to other orbits. The atmospheric re-entry, until about a few years ago, and burning up everything was thought to be the best idea. But nowadays, we are talking about thousands and thousands of satellites to be, deorbited and every year, and which will burn up in the atmosphere. And we have no clue right now what's going to happen with, let's say, the residuals from these objects, in particular the chemistry in the upper stratosphere. We have no idea. So we will have to investigate a lot into finding out what's going to happen. Perhaps this requirement of post-mission disposal is creating another issue, for example, in the upper atmosphere, in the ozone layer, or whatever. We don't know. So key elements, again, we have to manage the current population. What do I mean by manage? Removing massive objects from space. We call that active debris removal. It's nothing else than going up with a robot, take out one of these massive objects and let it burn up in the atmosphere. We can try to prevent collisions between large debris. I will mention that. The catchword is just-in-time collision avoidance. For example, by nudging them a little bit with lasers. Current activities are mostly focusing on this collision avoidance. It's a good thing to do. You should try to avoid any collision with an active spacecraft, but we have to be aware that the long-term evolution of the environment is driven by collisions of non-maneuverable objects, of these massive, for example, objects where we would need some just-in-time collision avoidance technology. We're far from having them in place. Technical issues, when we want to do collision avoidance, we have to ask that all objects should be maneuverable. All objects should do post-mission disposal. and the larger ones with controlled re-entries, because some of the pieces of larger objects might survive the fiery re-entry, and they could fall on our heads. I mean, this sounds, trivial, but frankly speaking, many or most of, let's say, the small satellites nowadays launched by academic institutions, or which we call them CubeSats, 10 by 10 centimeters, or even of some of the constellation of the startups which are deploying constellations of 3-unit CubeSat whatsoever. Almost all of them are not maneuverable. So they cannot do collision avoidance maneuver. They cannot do post-mission disposal. Then our current catalogs are by far not sufficient, not accurate, not complete enough to do a good job on collision avoidance. And yeah, it goes hand in hand with the fact that we have very limited capabilities to detect, track, and identify, as well as to predict the behavior of orbital objects in a timely fashion. So just one word or two words about, the legal framework. I'm very often asked, is there no rules? I mentioned this guidelines from the United Nations. These are at the top level. These are kind of principles which states are, signing up to. But then, actually, there needs to be national legislation. There needs to be space law in each and every country. And these laws would perhaps, for example, prescribe or demand that in order to get a license to launch your satellite under the flag of, I don't know, Switzerland or the United States or Russia, you need to comply with a set of, guidelines or with a set of norms and standards. So that's the lowest level. The industry has to comply with a set of norms. And some of these norms, for example, are about prevention of space debris, or mitigation of space debris. So this is how it works. But, only a small number of countries has legislation in place. And then, moreover, what are the incentives or the penalties for the operators if they don't behave, according to what they have been signing at the moment when they got the license? So space safety and sustainability go together. On one hand, we are talking about the environment, and on the other hand, we are talking about the safety of missions. So the core of all of that is surveillance and tracking. So we need to know where these objects are. We need regular tracking. We need to characterize this small size but lethal population. Then there is the environment. This is, the core topic of sustainability. So there we need the statistic population evolution models and, mitigation rules, post-mission disposal rules, active debris removal, and finally at the bottom, darkened sky and quiet skies protection. So we need rules and regulations on that side, but also on the other side where it is about the space traffic coordination. This is about the active objects. So we need to have systems in order to issue safety messages. Hey, you are on a collision course. Who is going to move? What are the standards and the rules of the road up there? What are the norms of behavior? This is more also, in the gray zone between safety and security. Rules, norms of behavior. If you're approaching another asset at a certain point in time, this will be looked at as a hostile action, but there's no rules right now, and different states are claiming others that others are doing hostile actions and so on and so forth. And we need standards and best practices, of course. So with that, in order to make sure that we can still fly in future these kind of nice space stations, that's not the only important thing we fly up there. I usually tend to explain that there is much more than is usually known in the public, which is flying up there, from which our societies really depend in a critical way I mean, each and all of us knows navigation satellites. We're using our cell phones all the time to navigate. But in another way, for example, more than 60% of the data which we use for the climate, let's say assessment of the global warming, is coming from space. Just another example. So in order to do that, and you see here, this is a historical picture. Actually, it's the last flight of Endeavour, and what you see is the robotic arm, which is inspecting the tiles, the heat tiles of the space shuttle, in order to make sure that he can safely return home. And the highest risk for these heat tiles, apart from the launch phase, is actually orbital or space debris while it's up there in space. So we need stringent international rules and mechanisms to ensure the enforcement of these rules. The mechanisms could be, incentives on the one hand, there could be penalties on the other hand. And scientific research and these type of observations are the foundation to measure the efficiency of such rules, the efficiency of the implementation of the existing guidelines and norms, as well as providing the rationale for new recommendations. We need to make sure that the new rules or new recommendations are providing the most efficient way of mitigating space debris. And the only way of verifying, validating that is having a look at it, and this is scientific research. So with that, I would like to thank you for your time.
Thank you so much, Thomas, for this enlightening presentation. Although the picture is darker, even darker than what I thought regarding our future. So with this, I open the floor for discussions. And again, if you have questions, please write them in the question and answers menu you have, and I'll be going through them. So we have a couple of questions by the same person, by Shiba. So the first one is about, I'll read them aloud. It's about space sustainability. How about this objective of creating solar panel farms? Is it possible with all the debris in space? And the question that comes with it is, how about space tourism?
Yeah, thank you. Thank you for this question. So we have to be aware that the risk of having a collision in space is increasing with the cross section of your spacecraft or whatever. We have currently the asset with the largest cross section is by far the International Space Station. And we see the effects of impacts on the International Space Station. There is, holes and impacts everywhere. Fortunately, none of them was catastrophic right now. The space station is moving several times a year to avoid an impact with a larger object. So if we're talking about large farms or large solar arrays, the risk is on one hand for the solar array, of course. You could perhaps mitigate so that you have smaller sections, so that you have only a small section which is knocked out by an impact. On the other hand, you will have a lot of secondary debris. So if you have a large surface, this is a space debris collector, and it will create more debris when being impacted. Then human space flight or commercial, space tourism, that depends a lot on how long you stay up there. The point is simply, the risk is is the product of the flux of space debris, the density of how many space debris are there, the cross section, and the time you're exposing that cross section to that flux. So space tourism, let's say if we're talking about a day or two or three, the risk is still minor compared to astronauts or cosmonauts which are living in the space station for a year or more. The major risk for tourism or even ballistic flight is actually the small size debris, because these assets or shuttles, they're not protected for debris larger than a millimeter or two, and the highest risk comes from that millimeter population where we have already a pretty high density in the lower Earth regime. So I wouldn't say a high risk for a mission of 1 to 2 days, but if you're talking about longer missions, then for sure this will increase dramatically in the near future.
Okay, thank you for that. So there's another question by the same person, Shiba. It's about space weather impact on satellites regard to increased risk. So in collisions, I'm not sure if this is about space weather impact that could cause the satellite orbit to lose altitude, or about, for example, energetic particle events that could hamper or prevent maneuvers because it's damaging the spacecraft. Well, let's take both.
Yeah, I mean, this is typical. Both effects are typical for space weather events, and let's start with the particle impact, which are dangerous for the electronics. That could prevent can prevent that you can control your satellite, and then it becomes a debris, or can prevent that you can do a collision avoidance maneuver. This is a high risk, especially for, let's say, these new small size satellites in high numbers. Why? Because traditionally, the large birds, they have been carefully protected for radiation events. You use just radiation hardened electronics, you have your redundancies, and so on and so forth. The new space approach is rather, take off the shelf. They will probably survive. Many don't, especially these small academic satellites. So there's much higher risk for these, I would say, from radiation events. If we have a prediction of a large event, then traditionally operators go into a kind of a safe mode, so that even if they have a plasma event, that their satellite is in the safe mode and has more chances to survive. The problem is not just that the electronic survives. If you are in a full attitude steering mode or whatever, then if you have a hiccup in that attitude control computer, it could, the effect could be that the satellite is starting to use its thruster to counteract something which is not happening. It's just in the computer, a hiccup. So that's why we use the safe mode. The other effect, in the atmospheric density, that's something which is very well known, by the way. And there's this, story of a whole series of, I don't remember, 30 Starlink satellites which were not reaching orbit. They were deployed, but during a time frame where there was a high space weather activity and the atmospheric density was high, and their electric thrusters were not able to move them out of this lower atmospheric layers. Nice story, but sorry, they could have known that because it was predicted. As simple as that. The other point is, the current knowledge about the atmospheric densities is very limited under normal circumstances. I'm talking about an uncertainty of plus minus 20% for the atmospheric density. While we have one of these huge events, the uncertainty is then factors, which makes it difficult to propagate satellite orbits. You have a measurement, the satellite is here, you propagate that orbit or one orbit or two, you have the next measurement, and oops, the satellite is not anymore there where you predicted it. And you have a huge difficulty and challenges to maintain your orbit catalog. This has been seen several times, where hundreds of objects were lost after such an event for several days, because until you could safely assign, a measurement of the object to the known object in the catalog. That's the second, main effect of let's say, space weather.
Okay, thank you for that. So there's a question by Ingrid Knossen, and are you aware of the research on climate change in the upper atmosphere and its impact on space debris? In short, increased
Yeah.
CO2 concentrations cause cooling, contraction, and this increases the lifetime of space debris and low Earth orbit.
Yes, yes, I'm aware of these studies. Sure, it's from both sides. There's the space weather on one hand, which may change the density of the upper atmosphere or the extension or inflation of the upper atmosphere. And the same thing, of course, climate change may have an impact on that as well. Again, I would say, these are things which are known. You have to design your orbits that you know how much fuel you need to maintain the altitude. You go higher up if if the atmospheric density is increasing in the lower part. I don't think that this is a major issue for long-term sustainable use of outer space. I guess the other thing I mentioned, the impact of demising spacecraft in the upper atmosphere and the impact on the upper atmosphere is probably more of an issue. We simply don't know.
Okay. So a question by Veronique Dawn. I've heard that there are some movements at the EU level with laws in the pipeline, and in view of the needed regulation, that would be helpful, of course. And do you see any future developments in this direction?
Oh, nice to hear, Veronique, that you're among the audience. um, yeah, very good question. Um, yes, of course, the European Union is trying to come up with its own regulatory framework. And I guess, Veronique, the main problem there is that in principle, at the level of the European Union, it's not at all clear if the Union could come up with a space law, which would be, mandatory for the individual states, because at that level of these laws, in principle, it's not the Union who can come up with the laws. It has to be done on the national level. It would be, from my point of view, very, very good to have, this kind of legal frameworks or even just guidelines at, the international level, because this also gives us a stronger handle with respect to the operators, in terms of forum shopping, for example, if you have one voice in Europe. And if you want to start in Europe, or if you want to broadcast over European countries, for example, Starlink, they need a license to broadcast over each and every country. And you can't tie that license to compliance of Starlink with whatever rules you want to impose. And it could be that these rules are the European space debris mitigation rules. Yes, I'm very much in favor of such rules. I'm a bit, let's say, skeptical right now if we are going to achieve that at the European level in due time. Because if I look at individual countries, Germany doesn't have a space law yet. And they're working on that law for years already. And in Switzerland, we are just about, to have a first draft of the space law, hopefully by this month or by next month. But it will take a long time.
Okay. So I see that someone has his hand raised, Neophytos Mesios. Veronique, can you unmute him? Yes. Neophytos, you can speak up if you have a question, because I didn't see it in the question answers. Neophytos, you're allowed to talk if you want to ask your question.
I think I didn't raise a hand, so I think it's a mistake.
Oh, okay. In that case,
sorry.
So I had another question from my side then, is that I used to hear that NORAD was the only system that was systematically tracking lots of debris above a certain size. Is this feature really unique? Or, I mean, if someday a country like the US or another country decides to stop sharing this information, would other countries have the capacity to take over and to pursue such a monitoring?
It's a very good question. And it's true that, let's say, until about, what shall I say, 15 years ago, um, there were only two systems in the world probably capable of monitoring a good percentage of the larger objects. And what you're referring to, the NORAD, or this is the US, or was originally North American system, Canada and United States. It's currently the US system, which is composed of a whole set of radars for low Earth orbit and optical telescopes for higher orbits. This catalog is probably still by far the most comprehensive catalog. It doesn't contain all the objects for sure, because there's so-called classified objects, military objects, which, as I mentioned, there's still this idea that you can hide in space. It's, from my point of view, a very much outdated idea. But anyway, it's not complete. And there's a public part of this catalog. And there is, bilateral agreements that you get some more information, you get collision warnings, and so on. But the question was a different one, is anybody else able to do that? And I mentioned the Russian system on one hand, and there is a Chinese system. Both of these are, pretty capable for sure, but there is no public catalog from these systems. So we cannot really assess what's really the completeness of the catalog. The picture changed very much in the past years in two ways. On one hand, for example, there's many countries setting up their own smaller systems, like Japan, India right now, and Europe. In Europe, traditionally, France was the pioneer. They came up with a radar. I don't remember exactly, almost 20 years ago, a phased array radar, which was capable to see objects of 1 meter at 1,000 kilometers, and they have improving that. So it's by far not as complete as what the United States can do. Just recently, we have private companies which are providing data. We have a private radar data provider, which is based on the data is based on their own radars, Biolabs in the United States, which are really having a pretty complete catalog, private actor. The same on the optical, there's a lot of optical telescopes. Here in Europe, we have the EU, the European Union Space Surveillance and Tracking System, which is, an association of some countries which are pooling their data from radars and optical sensors. And they have certain centers which are doing the orbit catalog or the collision avoidance messages and so on. So Europe has a capacity, just to name Europe, which is, of course, limited still, but it's growing. And as I said, the commercial players the commercial actors are playing a more and more important role in the game of data providers. Not in the game. Also in the game of conjunction assessment, and it is, but none of these commercial providers will easily come up with a full catalog. That is still going to be in the hand of governments for some time at least.
Okay. So if I move on, I have a question by Nina Bizian, who just became a doctor. Do we know
Congratulations.
Do we know the impact of the re-entry and the burn of spacecraft at the end of life on the atmospheric composition and the ozone layer and so on? As you mentioned, this is a timely topic.
This is actually something where we have no clue. And, at all ends. First of all, we have some, assumptions how much of the mass is going to end up as nanoparticles, for example, aluminum oxide nanoparticles. But that's just, guesses. We have no measurements actually. And even worse, we have no idea about the chemistry going up there at this altitude. We have some, of course, it took us a decade or two to understand what's happening with the ozone hole and what's the chemistry up there. My fear is a bit it will take us a decade as well to know more about the chemistry up there. Perhaps it's not a problem. Perhaps it's a huge problem. Compared to the influx from the natural micrometeorite, the mass-wise, this is still, it's still much smaller than the natural micrometeorite, but the material is different. Natural micrometeorite do not produce aluminum oxide, for example. So no, and this is the reason why I was really stressing the point, and the European Space Agency, just to give you an example, has a program now on that. They want really to support this type of scientific investigations. I think it's an obligation for all space agencies, because if we demand, the demise and even design for demise so that these satellites burn up, we have to make sure that this is not creating another problem. You could also think of the totally contrary. In future, because of that issue, we might perhaps ask for demise, but ask for designs which are surviving the re-entry, so that they're not burning up in the upper atmosphere. Then we have a problem on, on the surface of the Earth. We're going to dump them in the Point Nemo, but then we have the ocean people which would come up, hey, is this not the pollution of our oceans, and so on and so forth, which is less the case, but still.
Okay, so, and I will take one last question, because we have several questions. Is again by Shiba, is that actually it's about playing chicken, I guess. We have experienced agencies and companies having issues with collision avoidance. How do you see us resolving this issue with an incident with a satellite being forced to change its path as another spacecraft was approaching? And what are the consequences for countries not upholding to the laws in space for that?
Yeah. Okay, let's address the two questions separately. The first question is really about collision avoidance maneuvers. First of all, each and every collision avoidance maneuver is costing you currently huge effort in terms of person power. And it's costing you fuel, which is usually directly related to your lifetime. On top of that, during the collision avoidance maneuver, you cannot perform your mission. If it's an Earth observation mission, you cannot provide nice images. It's having an impact on your business. That's only one of the problems. The other problem is, the question, if you have two operational spacecraft, who is going to move? Are the measurements and orbits good enough that you can predict that well ahead, a day or two or a week, usually in low Earth orbit? Traditionally, you need more than a day to perform that maneuver. So we need new technologies so that we have onboard capabilities to perform a maneuver. I always tell people, at the limit, we need to be able to maneuver within half an orbit, which is 45 minutes. So you don't have enough time to upload commands, blah, blah, blah. You have to be prepared, and the maneuver has to be executed almost autonomously. No rules, right now, no rules of the road. Who has to move? Today you have to take the phone and call the other one or an email and ask. If you're lucky, you get the right person on the other side of the line, and then you're asking what are we going to do? Who is going to maneuver? Things like that. So we are in a situation where we have no rules, no norms how to behave in this case. It's totally different in the aviation industry. You have rules who is going to move, and you have a coordinating entity who is telling the planes, hey, you move up, you move down, or whatever. And what was the second question? The
related question was, what are the consequences for countries not upholding to the laws in space?
Okay.
Sorry.
Yes, yes. So the consequences are none, because there's a liability convention which was devised in the 60s as well. This is the only international convention which is talking about liability. There's also liability articles in the Outer Space Treaty, so you should operate with due regard, whatever this means, So the liability is the following. In principle, in space, if there's a collision and you're only going to be liable for the consequences if you have, only in case of gross negligence. And there the question is, what means due regard? Currently, there has been no case where this liability convention was called. That could change. We could say, oh, what means due regard? Due regard means that you have to be able to move your spacecraft. If you put a spacecraft up there which is not maneuverable, that's under the current norms not acceptable, let's say. But we are not there. So nothing is happening if a collision is taking place in space. The only, absolute liability is if an object falls on somebody's head. So others, there's an absolute liability, and it's not the liability of the operator, and that has to be very clear. It's always the liability of the launching state. So the launching state, if he's liable, and if he has no way of going back to the operator via license and contracts, then it's the state.
Okay, that's interesting. So I remember, I think it's 2 years ago, there were a couple of debris that re-entered the atmosphere nearby Spain, and the country of Spain decided to interrupt air traffic for a while because of it. So in that case, if they had to claim losses or so, they would turn to the country that launches the spacecraft.
Yeah, true. But I think they can only come up with a liability claim if property or life was harmed, and just having to close your airspace, you cannot claim that liability. Only if you have an impact on an airplane, if you have an impact on a house, or if some persons are harmed, that, of course. Property, yes. I mean, the only case where it almost came to a claim like this was when a Russian, let's say, spacecraft with nuclear material on board, was re-entering over Canada and left a huge footprint of radioactive material. So the claim was not there was no claim. There was simply, there was a reimbursement by Russia to Canada, ridiculous amount to clean up that area. But in principle, they could have gone to the UN and made a claim. So, but I mean, the problem is that these uncontrolled re-entries, in particular of upper stages, it's particularly massive upper stages where we know a lot of these pieces will survive the re-entry. This is nowadays, this is my personal view, this is totally unacceptable. It's totally unacceptable. You have to do controlled re-entries in any case where you expect, something surviving, not, being dumped or falling into areas where you can, which are inhabited, usually oceans, where you can then issue notifications to airmen and mariners. That's done, if you do a controlled re-entry. So it's really absolutely unacceptable, and it's taking place almost every week. It's mostly upper stages of some of the launchers.
Yeah. Okay, well, I think we could continue like that because it's a fascinating topic.
Sure.
I think we should probably stop at some stage. So let me thank you again very much for this very interesting talk, even though it is not very encouraging for community. And for those online, I just remind you that we have about one webinar per month on topics that are related to space sustainability in a very broad sense. And thank you all very much for attending, and thank you so much, Thomas, for this very interesting presentation.
Thank you, and thanks everybody for attending.
Thank you. Bye-bye.
Bye-bye.